Hey students, in this video we're going to cover limits of functions from tables and graphs. You might want to have a Desmos graph open because I'm going to be using it throughout the video. Okay, our first kind of example, or to get us talking about what a limit is, this is a example from mathisfun.com, and they use a geometry to describe this phenomenon. So we're going to look at a polygon. A polygon is any figure with sides inscribed in a circle. So here we have a triangle inscribed in a circle, a square inscribed in a circle, and so on. If we increase the number of sides, for instance, if we go from 3 to 4 to 1, 2, 3, 4, 5, 6 sides of a polygon, what can you say about the polygon with respect to the circle? Well, as we increase the number of sides in the polygon, I hope you can see that as the number of sides of a polygon increases, the polygon is getting closer and closer to becoming a circle. If we refer to the polygon as an n-gon, where n is the number of sides, we can make some equivalent mathematical statements. Each statement will get a little more technical. So I'm going to read these statements to you, and again, the more I read, the more technical we get. So as n, the number of sides, gets larger, the n-gon, the shape, gets closer to being a circle. As n, the number of sides, approaches infinity, the n-gon approaches the circle. And the limit of the n-gon, as n goes to infinity, is the circle. This is the vocabulary that we're going to be practicing. So the limit of something. So as I increase my number of sides in the polygon, as the number of sides go to infinity, the limit of this shape is a circle. How we write this in limit notation is we abbreviate the word limit to lim, L-I-M, and we say the limit of the n-gon, so the limit of whatever we're describing, as one thing changes, so in this case, as n approaches infinity, as the number of sides are increasing to infinity, then the limit is a circle. So we would say that this limit equals a circle. So again, we use the LIM to abbreviate the word limit. We're talking about the limit of something as the input changes, and what that limit is, we say it's equal to that. So let's take a look at a little bit more with the notation. So here it is in function notation and not geometry notation. We say the limit of a function f of x as x approaches c is the value L. And again, how we read this is the limit of f of x as x approaches c is a value L. If c, what we're approaching, is infinity or negative infinity, then this is describing the end behavior of a function. A few other notations and meanings. When you see f of x equals y, when you plug in an x value into a function, what you're getting out is a y value. So in the limit notation, when you approach an x value on a function, the output is going to approach a y value as well. So what this means is that the limit output will always be a y value, and we are going to approach an x value. So the output is a y value, and we're going to be approaching an x value. There are three kinds of limits. There's the limit of a function f of x as x approaches c from values below it. That's that negative sign. And again, that can equal a value L. So again, what this negative does after the c value is talking about a left-sided limit. To find a left-sided limit, we use values below the x value. For the second kind of limit, it's going to be read the exact same way, but now instead of a minus sign afterwards, you're going to see a plus sign afterwards. This is what we call a right side limit. And this uses values above or greater than the x value. And our last kind of limit is when you just see the x value that we're approaching all by itself as x approaches c. This is what we call the double limit, also sometimes called the overall limit. And what this is saying is that the left and the right side are the same value. So whenever you're doing a double limit, you're actually looking at both sides to see if they're the same. Okay, we're going to create a table and a graph for a function and then look at a couple different values. So number 1 says let the function f of x be equal to x squared minus 4 all divided by x minus 2. Find the following values. We're going to find f of 2. We're going to find the limit of the f of x function as x approaches 2 from the left. We're going to find the limit of the f of x function as x approaches 2 from the right. And we're going to find the limit of the f of x function as x approaches 2 overall. I'm going to quickly number these so that I can talk about them by number. Okay, I'm going to use the graphing tool Desmos to graph and create a table. You can also use a handheld calculator to do this if you would like. The first thing I'm going to do is type in the function. Once I have the function set typed in, to turn it into a table, I'm going to use the little pinwheel settings button, and then I'm going to click on the table setting. This gives me a table where I can input any x value that I want, and it will give me the y value on the function. It will also plot the function's value. I'm going to start with a fresh table, so I'm going to delete all of these values. And I need to move it around so that I can actually see the original problem. Okay, really quickly to talk about this function. This is a rational function that when reduced looks like a linear function. I'm going to zoom in on the actual function itself, because again, I'm only really caring about the x value 2 here. So I'm only really interested at the function when x is 2. So again, this looks like a linear function, but it is slightly different than a linear function in that it has an undefined value. For instance, if I type into the table, you can see that the value is undefined. And if I tried to trace the function with my cursor and I tried to actually go to this 2 point, there's an open circle hole there at that value. So this is f of 2, we say, is undefined. However, just because the value itself is undefined doesn't mean the values all right around it don't exist and aren't approaching the same thing. For instance, I'm going to start and I'm going to approach 2, but I'm going to be from below. So I'm finding the limit as x approaches 2, and I'm going to use values below 2. So I'm going to start with the value 1, and that value is 3. Let me move my table again. So when x is 1, the y value is 3. I can get closer to 2 than that if I use the number 1.9. And I can see that the y value is 3.9. If I use the x value 1.99, then the value is 3.99. If I add more 9s to that, it's going to be 3.999. And then I can continue to add 9s, and as I get closer and closer to the x value 2, the y values are getting closer to the y value 4. So what we can say about this is we can say the limit of the function f of x as x approaches 2 from the left-hand side is approaching the value 4. The limit is 4. Again, the limit is the y value based off of the x value that we're approaching. Okay, I'm going to clear out my table of values below 2, and now I'm going to use values above 2. Okay, I'm going to start with a value above 2. I'm going to start with the value 3, and when x is 3, the y value of the function is 5. To get close to 2, I can do like 2.1. 2.1 would round down to 2. When the x value is 2.1, the y value is 4.1. To get even closer to 2 than 2.1, I can add a 0 in the tenths place, so I can do 2.01. Again, that's even closer to 2, and then the y value gets even closer to 4 yet again. And I'll show you one more. If I do 2.01, 0.0001. This is getting even closer to 4. So again, as I'm using values bigger than 2, the x value is bigger than 2, the y values are still approaching 4. So we can say that the limit as x approaches 2 from the right-hand side of the f of x function is the y value again, 4. Notice we're talking about the value that it's approaching because I can always get closer to that number. So I'm not going to use the value 4.0001. I'm using the fact that it is getting closer to the value 4. And then the last thing that we can say is that as long as the left side and the right side are the same value, so because the left-hand limit is 4, the right-hand limit is 4, I can see that the overall limit or the double limit is also going to be a value 4. Again, the double limit is talking about both sides of the function. Okay, we're going to try another one of these. We're going to use Desmos again. We have a function f of x is equal to the absolute value of x squared plus 4x all over x plus 4, and we're going to find the following values. We're going to find f of negative 4. We're going to find the limit of the function as x approaches negative 4 from the left. We're going to find the limit of the function as x approaches negative 4 from the right. And we're going to find the limit of the function as x approaches negative 4 overall. Again, I'm going to number these just so I can talk about them in number. I'm going to go ahead and get my Desmos fully set up off camera. Again, I encourage you to do this along with me in a Desmos. Okay, I have my function in my Desmos calculator. I have the table connected to the function, and I went ahead and I typed in negative 4 for the x value. And again, just like the last problem, when x is negative 4, the function is undefined. The reason why I wanted to do this is sometimes the left and the right side of negative numbers can be a little challenging for students. One thing I want to say, so in number 2, we're finding the limit of the f of x function as x approaches negative 4 from the left side or from the less side. To be less than a negative number, what you really want to do is you need to be more negative. So a number less than negative 4 is negative 5. So when x is negative 5, the y value is negative 5. If I approach a x value, I want to get closer to negative 4, I can do like negative 4.1. And that's going to get me close to, that gives me the y value negative 4.1. Okay, then I'm going to do negative 4.01. And then to get even closer than that, I can add more zeros, negative 4.0001. Again, I am on the left side of the graph. If you notice, all the points are showing up on the left side. So here's negative 4. All the points are showing up on the left side of negative 4, which is why we call this a left-sided limit. Okay, so now to make our actual statement. As x is approaching negative 4 from the left side, the limit of the function is what the y values are approaching. The y values are approaching the value negative 4. So the left-sided limit as x approaches negative 4 from the left side of f of x is negative 4. Okay, see if you can pause the video and see if you can type in a table that would give you the right side value limit of negative 4. Okay, as I approach negative 4 from the right side, meaning I'm a little bit less negative than the value negative 4, my y values are approaching the positive 4y value. So as I approach the x value negative 4, but I'm on the left side of negative 4, as I get closer to that, the y values are getting closer to positive 4. So I can say that the limit of the f of x function as x approaches negative 4 from the right-hand side is the value positive 4. So now for the overall limit. The overall limit is saying, is the left side and the right side the same value? Are the two sides approaching the same value? Well, the left-hand limit is approaching the value negative 4. The right-hand limit is approaching the value positive 4. And so the double-hand limit, therefore, is not existent. So we use the abbreviation DNE, and this stands for does not exist. Any Mean Girls fans out there might know this from the iconic scene, the limit does not exist. And here is where we use that. The limit does not exist. Okay, there's a few times when we use D&E or does not exist for limits. Let's talk about what those are. Okay, the first time we use D&E is when the left limit does not equal the right limit. Then we say the double limit does not exist. So again, when the left does not equal the right, then the double does not exist. We just saw an example of this. Another way that this happens is, let's say your limit goes to infinity. So as we approach a number, we go to infinity. Then we can also say that that limit does not exist. An example of that in like a graph form would be a vertical asymptote in the graph. So let's say you've got a graph. Here's the value c, and as I approach c, I go up to infinity. This would be a vertical asymptote, and you can either say infinity or does not exist. And then the third and final way that this happens is when the values are inconsistent. So let's say as you get closer to 2 and the x value, you notice that the y values are jumping all around and never falling consistently on the same y value. Then we would say that limit does not exist. I'll do a quick little table of what that could look like. So here x is getting really, really close to the value 3, and the y values are kind of jumping all around. We would say that the limit as x approaches 3 does not exist. Okay, the remainder of this video, we're just going to practice reading limits from graphs. So we've got a graph. We don't have the option to have a table. They're not providing us a function, so we can't create a table. And so we need to be able to identify the limit just by looking at the graph. So in question 1a says the limit of the f of x function as x approaches 1. So the value that I'm going to be looking at is the value 1, and that's the x value that I'm approaching. Because there's no positive or negative out here, what's actually this means is I need to check both sides of my limit. So I'm going to look at the left side and the right side. To look at the left side, I want to be below 1 and I want to go towards 1. So I'm looking at the function as x approaches 1. I'm approaching this open circle here at the y value 3. I'm also going to check the right side of the limit. So I'm going to start at 2 and go towards 1 on the right side. And I'm going to follow that function the same way here. I can see that both of these arrows are pointing to the same y value. Even though that y value is open circle undefined, the limits are both approaching the same y value. So we can say the limit of the f of x function as x is approaching 1 is the y value 3. Try B on your own. Pause the video and check your work. As x was approaching -1 from both sides, the y values are approaching 1. Okay, this next example is given a graph. The graph is a linear function with a hole here at 2, 4, but a defined value at 2, 1. We're finding the limit on the f of x function as x approaches 2. Pause the video and see if you can find the limit as x approaches 2 from both sides on this graph. I notice that as x approaching 2 from the left-hand side, the y values were approaching 4. On the right-hand side, the y values were also approaching 4, so the double limit was 4. And then part B asks for what is the value of f of 2. Pause the video and see if you can find this value on your own. Okay, when we're talking about f at 2, we're talking about the closed defined point at 2, 1. So when f is 2, when x is 2, the value of f is 1. We can also use limits as a way to describe in behavior. So for instance, here I have the limit of a function f of x as x approaches infinity. Approaching infinity means I'm going to let the x values get larger and larger and larger, and then I'm going to see what the y values are doing. There's no two sides of infinity because you can ever be on the other side of infinity. So I'm going to start at the very end of my graph where currently I have 3, and the y value is just above 2, so maybe 3 and 2.1. And then as I go to infinity, what this horizontal line is saying is that there's some type of horizontal asymptote in this graph that's going to force my function's values to stay always just above the y value 2. So as x goes to infinity, so as I'm out here at like 100 on the x value, I'm still going to be just kind of above 2. As I go to 1 million, I'm still going to be just above that horizontal asymptote of 2. So as x approaches infinity, the function is approaching the value 2. Again, this is another way to describe in behavior. To do as x approaches negative 2, I'm going to start at the last x value. So here at negative 4, I'm just below 2, so maybe 1.9. And I'm going to approach negative infinity. So if I go to negative 10, I'm still going to be forced below that horizontal asymptote. As I go to negative 100, I'm still going to be forced just below that negative horizontal asymptote. So I can say that the limit as x approaches negative infinity is still that value 2, because I'm always going to stay right there at that horizontal asymptote.